So in this video, I'm just going to kind of go over a little bit of a thermochemistry problem where we're looking at a gaseous system that is isothermal, and that process is going to be reversible in this case. And so what we're going to do is calculate the work, the heat, the internal energy, the change in internal energy, and then the delta S of the system, the delta S of the surroundings, and then also the delta S of the universe in these instances. So overall, right, if we read the problem, a cylinder with an initial volume of 10 liters and has 1 mole of an ideal gas at 25 degrees Celsius, the cylinder is fitted with a frictionless piston and the gas expands to a volume of 20 liters. Assuming that the surroundings are large enough so that if heat is withdrawn from or added to it, the temperature does not change, right? So that's a very important thing to think about, right? So if you're working through a thermochemistry problem and it says that the temperature for the system isn't going to change, then that's going to tell you right then and there that you're looking at an isothermal problem, right? And so that's going to give you very specific characteristics that you have to think about in terms of being able to solve for it and identifying things, right? And so a huge characteristic of an isothermal problem is that right off the bat, you know that delta E is going to be equal to 0, right? There's no change in internal energy. Any heat that gets generated or lost gets converted directly into work in these problems. So we know delta E is going to be equal to 0. And so because of that, right, because delta E is equal to Q plus W, we can rearrange it. And so then that'll let us know that Q is going to be equal to negative work in that case, right? So they're going to be the exact same. So the way to approach this problem then is we can just simply calculate work, right? And so work in this case right here, because there's not going to be a change in temperature, right? So you're not going to be using any of the heat capacity problems. So work for an isothermal and reversible problem, in these cases, what you're going to be using is the equation negative nRT times the natural log of the final volume over the initial volume in these cases, right? And so if we write out what we all have, I'm just going to write it over here, right? So V initial is 10.0 liters, right? V final is 20 liters, right? The temperature we are at is 25.0 degrees Celsius, which is 298 Kelvin. And then the number of moles we have is 1.00 moles in this case. So if we just take all of those values and we just simply plug them into this equation, we should be able to solve for the work, right? So if we go in, right, we have negative 1.00 moles times 8.314 joules per mole per Kelvin times the temperature, which is 298 Kelvin, times the natural log of 20 liters over 10 liters in this case. So if we plug that in, what we end up getting in this case right here is negative 1,720 joules. And so easily, right, Q is just simply going to be equal to negative work, right? So if Q is equal to negative work, then that means we're at negative 1720 joules. So that comes out to a positive 1720 joules in that case right there. So easy enough. Now, the entropy parts of the problem. One thing to think about, right? So when we say that a thermodynamic process is reversible, right off of the bat, delta S universe is equal to 0, right? Any reversible process, delta S universe is equal to 0. Delta S system and delta S surroundings aren't necessarily going to be 0. But we know that in a reversible thermodynamic process, you're going to have delta S universe is equal to 0 if it's reversible, right? So we know that right there. And so we also know that delta S universe is equal to delta S system plus delta S surroundings. So if we know that right there, then that's just going to directly tell us, right, that delta S system is going to be equal to negative delta S surroundings in this case right here. So the way to approach this, right, delta S system, not delta S system is going to be equal to the heat, right, divided by temperature in this case right here. And so, another way that you can write this out is also as, right, if you take Q and you just simply relate it to the nRT natural log VF over VI type of scenario, right, what you can do is you can have nRT natural log of Vf over Vi divided by temperature, right? The temperatures cancel out. And so another way that you can approach this is just simply nR natural log of Vf over Vi. But because we already did all of the calculated Q, we don't have to go through that whole process, right? Only a situation where you don't know Q, or where Q still has to be calculated, right? You would probably want to go through that system right there. So I'm just going to simply take the Q over T here, right? I'm just going to plug in the value that I have up here, right? So Q is equal to 1720 joules divided by the temperature, which is 298 Kelvin in this case right here, right? So divide those two together, you get 5.77 joules per Kelvin, right? And that's going to be our delta S of the system. And then, right, because we know that delta S of the surroundings is equal to negative delta S of the system, right? What we can then easily do is delta S of the surroundings is equal to negative delta S of the system. So that will be equal to negative 5.77 joules per Kelvin, right? And so that's how you calculate those 6 different components of this problem right here.